Hello and welcome to our third video on our series on the math review for the course. This is perhaps the most important video since it reviews the concept of the Lagrangian and how we're going to use it and interpret its results. We're going to be going over these again and again as we move through different models of the course. So let's go into constraint optimization. The basic example is the one with which we finished the previous video. Many problems are going to be subject to constraints. The example we're going to cover the most, as I was saying, is that of maximizing utility. In this case, the utility of consumption and labor, subject to both a budget constraint and a time constraint. Now, to solve this problem, we first need a way to deal with these constraints, what to do about them. Just taking derivatives of the objective function fails to solve the problem because it ignores the fact that the agent has a constraint and hence a trade-off. In most cases, the constraint is the one that's going to tell you what the trade-off is about. The fact that you cannot have more consumption without getting more income, that's at the heart of the consumer's problem. And so, if you will just take derivatives of the utility, well, you will conclude that the agent likes consumption, the agent dislikes labor, and so perhaps what you want to do is consume a lot and do not work at all. That is clearly impossible, but we don't know that until we see the constraints. And so we're going to have two options. We can try to eliminate the constraints, get them away from the problem, or use the Lagrangian method and incorporate the constraints into the objective function to be able to solve the problem. Let's go through these two options one at a time. So eliminating constraints. This is often very easy for us because many of the constraints we face are linear. That's the case of the constraint we had before, the budget constraints. They are very easy to manipulate. In fact, this one is already ready for us to use. It tells us that the level of consumption, it's completely given by the level of labor. If you want to consume more, you need to work more, get more labor income, then transform that income into consumption. That's the only way. And so we could just replace that. We can replace into the objective, get an unconstrained problem. This new problem depends only on labor because the value of the constraint is implicitly given by the budget. The value of consumption is implicitly given by the budget constraint. And we can get the solution quite readily by taking derivatives. The first order condition that we can later interpret as the marginal benefit of working, given by the marginal utility of consumption times the wage. It has to be equal to the marginal cost of working. I don't want to dwell too much right now on the interpretation because we're going to get a much better interpretation in a moment. But, it suffices to say here that we've basically finished. We've characterized the equation that's going to tell us what the optimal decision of the consumer is. So what I want to tell you now is why you shouldn't be doing this, at least not in general. This is something that's going to be useful sometimes, but not always. It is generally easy to replace the constraint, but you cannot always do it. Sometimes your constraints are just more complicated. Perhaps they have many variables and you are not going to be able to replace enough of them out. Sometimes you're going to have many constraints and it's just not going to be clear which constraints to replace and where. This is actually going to be the case later on in the second half of the course when we're talking about monetary models. And so if relying too much in eliminating the constraints might prove impractical. It might actually make your life harder. The second reason why you shouldn't be just eliminating the constraints is that you are likely to be missing the intuition behind the problem and behind its solution. Replacing the constraint is a very effective method, but it treats the problem you're solving as a math problem and not as an economic problem. It distracts you away from the intuition and the interpretation, and it focuses instead on just mechanically how to solve the problem with math. And this is not a math course. We're using a lot of math tools, but we want to focus on the economics of the problem. And that's exactly why we want to use the Lagrangian. As I'm going to show you in a moment, and that's going to be most of the video, the Lagrangian method is going to let us go directly at the interpretation of the problem. And so let's talk about it. The basic idea is we want to solve a similar problem than the constraint problem we had, but in an unconstrained way. And so here we can see the typical problem we have is we're maximizing, choosing variables x and y. We want to optimize over some function f that we want to maximize, and we're subject to some constraint. The h function is just giving you the form of the constraint. The Lagrangian function, it's going to replace this problem by adding a Lagrange multiplier that we generally call lambda because L in the Greek letter for L, the Lagrangian, is going to be a lambda, times the constraint. And you're going to see this is actually a very clever way of transforming the problem. Now, before we go into the interpretation of the problem and why this works, let us see just how this looks in the case of our example before. We're maximizing in the Lagrangian, choosing consumption and labor, just as before. We had our objective function, which is going to be the utility of the agent. That's going to be our f. And then we need to plus lambda, the Lagrange multiplier, times our constraint equated to 0. So this is going to be the constraint here. Okay, so now some interesting properties of this. The first one is when the constraint is satisfied, so when h is exactly equal to 0, or in our case, when consumption is exactly equal to your income, the value of the Lagrangian is going to exactly coincide with the value of the utility. So you're actually just maximizing the objective function. The value of the Lagrangian, it's the same as the value of the utility when you maximize, when you're actually satisfying the constraint. So the constraint kind of goes away because it optimally has to be equal to 0. The second thing is that in order for this to have some representation, we always want to express the constraint so that it's weakly positive. The intuition for this is very simple. We can consume less than our income. You can let income on the table, but not the other way around. We cannot just consume more than the income we have. And so we always want the constraint to be weakly positive. That means we always want to express it as income minus consumption. And that's going to guarantee that our lambda is positive. In our next slide, we're going to see why lambda being positive is an important thing. If you go back to lecture notes from previous courses, you might find that instead of expressing the constraint as income minus consumption, you might express it as consumption minus income. By doing so, you also express this with a minus. By putting a minus here, you're actually getting the exact same expression as the one I'm showing you, but I'm going to avoid that minus and always express this as plus lambda times the constraint equated to 0. Okay, now the key here, as you can tell by now, is the Lagrange multiplier. The multiplier is the thing that's going to make the Lagrangian coincide with the problem we had before. And so here in the Lagrangian I'm showing you, we have already incorporated the constraint by multiplying it by lambda. Now we know already that the value of the Lagrangian, that curly L, it's going to be equal to the value of the utility. But what about the value of lambda? Well, that's the thing that we're going to focus on. Lambda is very important because it is the key to developing economic intuition of the problem. Now we need to do two things. We need to know how to interpret lambda, how to read it, and we need to know its units. As we go on in the problem sets, as we go on into further modules, looking at the units of variables is going to be super useful for us. It's going to be a key part of how we're going to know we're actually solving our problems correctly. Now, let's look at it here. A final thing I wanted to say before moving on to the interpretation of the units of lambda, sorry, I forgot about this, is this is particularly useful when you have more than one constraint. Because adding more than one constraint is easy. It's just a matter of adding more than one multiplier and then interpreting each multiplier separately. I'm actually going to show you an example of this later on. So interpretation. Let's talk about interpretation of lambda. Lambda is going to measure the value of relaxing the constraint, whatever that means. For now, we're going to be agnostic. Now, relaxing the constraint, I say whatever that means because it really depends on what you are constrained by. If it's a constraint of a budget, then lambda is going to measure the value of adding more income. If it's a time constraint, then lambda is going to measure the value of getting more time, and so on and so forth. So in our utility maximization example, lambda is the value of additional resources, of getting more income. But there's a catch. You can get additional resources in many ways. Lambda doesn't care about how you got those additional resources. Lambda allows you to price any type of income. And here we can see why lambda is so important. It works exactly like a price. It is the way in which the person taking a decision prices additional income or additional time. And once we know how to price things, we better understand how to make decisions. So let's talk about the units. Well, the units of the multiplier, as I was saying before, are going to matter a lot when reading our first order condition. But because they matter to read the first order condition, being able to check these units is also a great way of knowing if your derivative is correct. Many times as students, the problem that we're going to face is we take our first order conditions, it's a big math problem, we take the derivative. How do we know if we did it correctly? How do you know in the middle of an exam, did I take this first order condition right? Am I taking derivatives right? Well, paying attention to the units, it's going to help you know that. Because if the units don't match, then you know there is an error. So catching errors is super important in order to be able to solve problems, especially problems you haven't seen before. Well, the units are of course going to depend on what we're pricing with lambda. In our utility maximization example, lambda is going to be measured in utils because that's your payoff. Your payoff is in utils per unit of income. This should make sense. If lambda is the price we give to additional income, well, it's asking us how much do we value additional income. The value is given by utils. So lambda is measuring utils per unit of income. But note, in our problem there is no money. Because there is no money, income is directly expressed in units of consumption or units of output. Now, because units of income are equal to units of consumption, then lambda is expressed in utils per unit of consumption. But that's a definition of the marginal utility of consumption. So in our case, lambda gives the value of the marginal utility of consumption at the optimum. And this is great for us because it already tells us what we should expect. We haven't taken any derivative here for this problem, yet we already know what the value of lambda should be just by looking at the units, just by looking how should we read this variable. Now, let us try to do the interpretation once we take all the first order conditions. So here is the same problem we had before. This is the same Lagrangian we were working with. These are the two first order conditions of the problem, the one with respect to consumption, the one with respect to labor. Now, from the first condition, well, we just get what we already knew. This condition, if you see, it's telling us that lambda, it's exactly equal to the marginal utility of consumption. So now, we've confirmed that the first order condition is providing us the same interpretation we were expecting to get. The second condition is way more interesting because it gives us the key trade-off of the problem. And we can read this condition in different ways depending on how we want to write it. So I'm going to interpret it for you in two different ways. The first interpretation is in terms of utility. So we're going to be thinking about trade-offs directly in terms of utility. Well, what do we get? First, let's check the units. V prime of L, that's the marginal disutility of labor, is measured in utils per unit of labor. How much utility do I lose if I work an additional hour? Now that's important because if one side of the equation is measured in utils per unit of labor, then in order to be comparable to the other side also has to be measured in utils per unit of labor. Let's take a look at that. Lambda, as we just discussed, is utils per unit of income. So how much utility do I gain if I get an additional unit of income? Wages, well, the wage is measured in income per unit of labor. How much income do I gain if I work an additional hour? And so when we multiply them, lambda times W is measured in utils per unit of labor, just as we want it. How much utility do I gain if I work an additional hour and consume the income I receive. Now, this is important because just by looking carefully at the units, you not only know that you've expressed the equation correctly, you're basically spelling out the interpretation you want. One side of the equation is telling you how much utility do you lose for an additional unit of labor, for an additional hour. The other side of the equation, I'm going to the last bullet now, is how much utility do you gain if you work that additional hour. And so you already know that you're basically trading off utility you lose because you're working more with utility you gain because that work is allowing you to consume more. And that's the basic trade-off of the problem. And that's what we get with the interpretation. The market values my work at W, and I value that income at lambda. So lambda times W is the price of labor in utility terms. Because I'm a price taker, that value is fixed for me. So how do I compare that with the disutility of working? Well, if the disutility of working is less than lambda times W, I am receiving more utility from my labor than what I'm losing in this utility for working. So I should work more. But as I work more, I still get the same utility for my work, lambda times W. But the cost is increasing because I'm working more and more. Now, I'll keep working though up until the value I'm getting for that additional work, it's equal to the disutility, to the value I'm losing for that additional work. And that's the optimal, just as we were seeing in our first video. Now, the second way of interpreting this problem is in terms of units of income. Okay, let's think about it very quickly. We can re-express the same first order condition by dividing both sides by lambda. Now, we know that lambda at the optimal has to be equal to the utility, the marginal utility of consumption. And so that means that now we've equated the marginal rate of substitution between consumption and labor to the wage. So how do we think about it? Let's first go units. The MRS, the marginal rate of substitution, well, V prime is utils per unit of labor. U prime is utils per unit of consumption, or units of income, because consumption and income are expressed in the same units. Then their ratio is measuring units of income per units of labor, or equivalently units of consumption per units of labor. This is important though, because it's telling you how much consumption, or equivalently income, do I need so as to be compensated for an additional hour of labor. This is the rate at which the agent, the consumer, is willing to trade labor for consumption, for income. It's telling you how much additional income do you need for every unit of labor you spend so as to remain indifferent. Now W is much easier. It's directly measuring income per units of labor. And so it's exactly comparable to the MRS. You can see how just going through the mechanics of which units we're measuring things in already gives you a lot of insight about how you're going to go around and interpret this condition. Okay, when we do the interpretation, you can see it follows directly from the units. The market value of my work is W. The market gives me W units of income or consumption for each unit of labor I provide. This is fixed to you as a price taker. The marginal rate of substitution is the rate at which you are willing to exchange labor for consumption. If you get exactly MRS units of consumption for 1 unit of labor, you break even. Your utility does not change. But if you get more than that, if you get more than what your marginal rate of substitution is requiring, then actually you're more than compensated, and so your utility increases. That's exactly what we're going to see. If the MRS is less than W, then the market is giving me, as a worker, more consumption than what I need to maintain my utility. I should work more. But as I work more, I get paid the same. But I get more consumption to break even. I need to get more consumption to break even. And so the cost of working increases and the utility of that additional consumption gets lower. That's why the marginal rate of substitution is going to increase. And so you keep working up until the marginal rate of substitution is equal to the wage. Okay, that's going to be the ultimate conclusion of this. And that's the second way in which we can interpret the utility. Now, the last part of this video, it's a simple aside about how to think about the marginal rate of substitution as coming from indifference curves. So here is the key. An indifference curve is just defined as pairs of consumption and labor that give you the same utility, say a value u bar. Now, if that's the case, then you can take the total differential. Now, u bar is a constant, it's some constant value of utility, so it doesn't change. That's this left-hand side here. It's a 0 because the utility is not changing. And the right-hand side is telling you how much are you changing consumption times the marginal utility of that consumption. That's how much utility you're going to get. That has to be compensated exactly by a decrease in utility coming from labor. You can reorder terms to get exactly the definition of the marginal rate of substitution. This is the left-hand side over here, being equal to how much consumption has to change relative to how much labor changed, so that utility here is constant. And so that's why we've been interpreting this. And that's also why when you go back to the book that you should be going over, when you go back to the book, you're also going to get an interpretation of the marginal rate of substitution graphically from the slope of the indifference curve. Finally, some thoughts about interpretation and why I'm spending all this time thinking about how to interpret the first order condition that you've been getting again and again in all your previous courses. Well, it's really worthwhile to spend time reading them, just looking at how they are. You can probably solve them without all these steps. And if I give you a functional form for the utility or a value for profits and a value for wages, you can mathematically solve for this solution. You can mathematically solve for the optimal value of consumption, the optimal value of labor. But you should feel comfortable interpreting first-order conditions in terms of marginal benefits and marginal cost. In part because I'll be asking about it extensively, but more importantly because this interpretation is key. It's what you take out of econ classes. Thinking seriously as an economist about how do people make decisions, what are the things that they have to take into account, what are the potential trade-offs, how are they pricing different things, different alternatives. That's what you're taking out of this. So I will not focus on numerical problems. We will not be solving for the value of consumption. What does it matter if consumption, optimal consumption is 5, if it's 10, really what changes? What I'm worried about is what you're gonna be doing with this out of the class. Knowing if in an example consumption is equal to 5, it's probably not gonna change your life. I do hope that learning how to think seriously about trade-offs and how to price stuff, that's something that you can carry on and use in other classes or later as professionals. So the objective I'm gonna be focusing on is interpretation. Again and again, as we go through different problems, I'm going to be focusing on that. Thank you.